So, in continuation to the earlier lecture in which we have discussed using nested interval property, that how to prove that set R of real numbers is uncountable. So, let us again quickly recall the statement nested interval property, that if In is equal to closed interval a and bn is a sequence of closed and bounded intervals, closed and bounded nested sequence intervals, then there exists at least one real number xi which is common to each of the interval. And when this xi will be unique, if infimum of the length of such intervals, such nested sequence of closed and bounded intervals, then this xi will be unique. So, this part we have already done. Now, we will cover representation of real numbers. So, let us start with the known one, the decimal representation, the real numbers into binary form as well as ternary form. So, if we will start representation of real number, representation of real numbers into decimal form, So, decimal form means we need to use the digit from 0 to 9. Using this, I need to do a representation of real number into decimal form, then we will see that this representation is unique. Using again the nested interval property, we will see that this representation is unique. So, we will start from any x belonging to 0 1, because once we know the decimal representation in 0 1, add or subtract real numbers for any other representation by translating it. Now, let us try to understand with the help of some example. We know that half has two representation, one has 0.4, 999 and so on, all digits ending in 9, and another representation is 0.5 and then it's ending in zeros. So, from question is from where we have such representation, what is the technique to do this? So, we will start with this unit interval. Suppose we have any other number, say 5.5. So, if I know the representation for x equal to half, say 0.5, then I can add 5 to it and we will have the representation of 5.5. And if boundary points are there 1, if we take 1, then I can write 1 as 1.000 and 0 as 0.00 and so on. If any real number is between 0 and 1, so it will have decimal form. For example, this half we have here 0.4999. So, let us do from where we have this one. So, we will start from the unit interval, say 0 and 1, and since we are interested in decimal form, so we will write 1 as 10 by 10, and 0 as 0 by 10. We will divide into 10 equal parts, say 1 by 10, 1 by 10, 2 by 10. For the sake of explanation, I need to write all this: 3 by 10, 4 by 10, 5 by 10, 6 by 10, 7 by 10, 8 by 10, 9 by 10. Let us label each one of this. If any real number is between 0 and 1 by 10, then we will label it by 0, 0. If any real number is in between 1 by 10 to 2 by 10, then we will label it, we will assign the number notation 1, digit 1. If any real number is in between 2 by 10 to 3 by 10, so we will assign it as 2, 3 and so on. And here we have 3, 4, 5, say 4, 5, 6, 7, 8 and 9. So, we have 10 partition of interval labeled from 0 to 9. Now, I need to represent half into decimal form. Now, if we notice, then half is this one, 5 by 10. Half is basically 5 by 10, and 5 by 10 is on the boundary of the interval denoted by 4 and 5, that is from the interval 4 by 10 to 5 by 10, it is sharing the common boundary between 4 by 10 to 5 closed interval 4 by 10 to 5 by 10 and 5 by 10 to 6 by 10 labeled as 4 and 5. So, in this for 1 by 2 we have two choices, either I start with this interval denoted by 4 or this interval denoted by 5. This is the reason why at the first place we have 4, at the first place we have 4 here. If we choose this interval 4 by 10 to 5 by 10, and if we choose the second one labeled as 5 from 5 by 10 to 6 by 10, then we have the first digit here as 5, first digit here as 5. Now, let us take this one 4 and again divide into 10 equal parts 4 by 10. This part I have taken from 4 by 10 to 5 by 10, and let us draw here 4 by 10 to 5 by 10, 5 by 10. Since we again need to divide into 10 equal parts, so I can multiply numerator and denominator for the sake of explanation. It will be 50 upon 100, 50 upon 100, and this will be 40 upon 100. So, the next term will be 41 upon 100, 42 upon 100 and so on, 42 upon 100, and the last previous one will be 49 by 100. Again label it by 0, box 0, this one by box 1 and the last one as box 9. Now, again we need to see that 1 by 2 lies in which of the interval. So, 1 by 2 I can write it as, if we multiply 1 by 2, 1 by 2 will be 50 by 100, 50 by 100, and we can observe from here that 50 by 100 is the last point of the interval denoted by 9, labeled as 9, that is from 49 by 100 to 50 by 100. So, the next digit will be 9. This is because we have started with this interval labeled as 4 and then again divided into 10 equal parts. So, we will label it by 9. This is the reason why next digit is 9 here. Now, if we keep on dividing this interval, say 49 by 100 to 50 by 100, if we keep on dividing this interval, say 49 by 100 to 50 by 100, again in 10 parts, 50 by 100, then basically this one is the number half. So, again if I multiply it by 10 in numerator and denominator, I will get 500 upon 1000. So, this is half 1 by 2 and this will be in the last of the interval labeled as 9. So, if we keep on dividing again and again, it will this number half will be in the last of the slot labeled as 9. This is the reason why after 4 every entry is 9. So, this is one of the representation which we have started from this interval by selecting this interval 4 labeled as box 4, that is the interval from 4 by 10 to 5 by 10. If we select this interval say from 5 by 10 to 6 by 10, so we will observe that 1 by 2, because it is the let me write here. So, let us select this interval say 5 by 10 to 6 by 10, 5 by 10 to, and keep on dividing to 10 equal parts. So, I can write this by 60 by 100 and this I can write as 50 by 100. So, the next point will be 51 by 100 and so on, 52 by 100, 52 by 100, and this point will be 59 by 100. So, again label it by box 0, this by box 1 and the last will be box 9. So, we can observe that 50 by we can observe that here 5 by 10 or say 50 by 100, this half is basically 50 by 100 here. So, it lies in the first part and also it is the extreme point of this interval. So, if we keep on dividing, it will always be in the first part. This is the reason why the rest of the digits, or we can say that it ends in zeros. So, whenever there is a so what we have observed from here, that whenever there is a real number and that real number shares the common boundary, then after some digits either all digits will be, and we are writing in decimal form, then after some digits either all digits will be 9 or all digits will be 0. Similarly, in ternary form we will see that because in ternary form we used to write either by the digits 0, 1, 2 or one can choose the symbol -1, 0, 1. So, if we choose the symbol 0, 1 and 2, then and there is any real number which is sharing the common boundary, then after some digits either all digits will be 0 or all digits will be 2. And if we are in binary form, suppose we are doing it with the using those two symbols 0 and 1, and there is a real number which is sharing the common boundary of the interval, then either after some finite digits all digit will be 0 or all digits will be 1. So, this is the representation of half, but each of them basically these are the series. We can write into series form, and later on we will see that both the series converge to half. So, let me do it again on next page. So, we have seen that in decimal form we have two representation for half, that is say for half we have 0.999 and so on, and 0.5000 and so on. So, this one is 0.5 already. This series will again terminate to half. How? Say 0.4999 and so on. From where we have this 4, I can write into series form as 4 by 10 plus next digit is obtained when we again divide by 10. So, I can write it as 9 by 10 square plus this 9 will be obtained when we again divide into 10. So, it will be 10 cube and so on. So, we can see that we can write it as 4 by 10 and we can take common here, say 9 by 10 square, then 9 by 10 square, the first term will be 1 plus 1 by 10 plus 1 by 10 square and so on. And we can see that this bracket is basically a geometric series with common ratio 1 by 10 and the first term as 1. Since this one is an infinite series with common ratio less than 1, so I can do this calculation 4 by 10 plus 9 by 10 square into a upon 1 minus r. So, first term is 1 upon 1 minus common ratio is 1 by 10, 1 by 10. So, after simplifying it will be 4 by 10 plus 9 by 10 square into denominator will be 9 by 10. So, I can write it overall as 10 by 9. Now, this 10 get cancelled out, 9 get cancelled out, we have 4 by 10 plus 1 by 10, that is 5 by 10, or I can write it as half. So, both the series here we have seen that every representation can be expressed into a series form, and whenever there is a real number which will share common boundary to two intervals, then both these representation will converge to the same real number. There are several cases, parallel cases in ternary representation as well as this binary representation. Similarly, in your book by R.G. Bartley, the book of real analysis, there is one more example given on page number 51. You can do it by yourself, that if for y is equal to 38 by 100, y is equal to 38 by 100, again this has two representation. This is common to two such intervals. So, if you use the similar process, we will get 0.37999 and so on, and here we have 0.380000 and so on. So, again one can observe here that after some finite step, either whenever this is sharing the common boundary, then after some finite digit either all digits will 9 or all digits will be 0. This we will use in to prove that 0, 1 is uncountable. Similarly, let us do one more example. This is the explanation for decimal representation. Later on we will using nested interval theorem, we will see that such a representation is unique, and in case if it is not unique, then after some digit either all digit will be 9 or all digit will be 0 in decimal representation. Now, binary form. So, we know that in binary representation we need to use only 2 digits. Let us denote it by 0 and 1, and suppose we are interested in, question is convert 3 by 4 into binary form, into binary form. So, we need to use the same technique. What we will do? We will start with the unit interval, say this point is 0, this point is 1. Since we need in binary form, we will divide into 2 equal halves, just like in decimal system we have divided into 10 equal half. So, I can write the end point as 2 by 2, this one as 0 by 2, and so the middle point will be 1 by 2. Label it as box 0, this one as box 1. So, we have 2 interval, one from 0 by 2 to 1 by 2 labeled as 0, and box 1 from 1 by 2 to 2 by 2 labeled as 1. Now, where will be 3 by 4? In the first interval or second interval? So, 3 by 4 into binary form has two representation. Why it has 2 representation? Let me first write those representation. It has representation as 1 0 1 1 1 and all digits ending in 1, and another one as 1 1 and all remaining digits ending in 0. So, from where we have this, let us try to understand this one. So, in the first case 3 by 4, I can write 3 by 4 as say 1.5 upon 2, 3, I can express 3 by 4 as this one. So, 2 here denominator is 2, but numerator is greater than 1. So, obviously, this will lies in this interval. So, its first representation at both places is 1, because it is lying in the interval 1 by 2 to 2 by 2, and which is labeled as 1. So, in both representation the first digit is 1. For the second digit again we need to divide into 2 equal halves. So, select this interval 1 by 2 to 1 and divide into 2 equal halves. Let us select this interval 1 by 2 to 2 by 2. Again we are going to divide into 2 equal halves. So, let me write it as 4 by 4 and this one is 2 by 4. So, the middle point will be 3 by 4. Now, here we can observe that 3 by 4 is now sharing the common boundary of both the intervals labeled as 0 and 1. This means we at second place we have 2 choices. This is the reason why here we have 2 choice. At this place, if we choose this interval, then we need to write 0 here, and if we select this interval, then we have 1 at the second place. Now, if we select this one, suppose we select this one 0, then just similar to the case of decimal system, here 3 by 4 will be end point of the interval 0 denoted by 1 by 2 to 3 by 4. So, again if we keep on dividing this into 2 such intervals, then 3 by 4 I can write it as 6 by 8. So, it will be always in the last part of the further division. So, all terms will be 1, all terms will be 1. I can write it as 2 by 4 and this one as say 3 by 4. I have taken this one labeled as 0. So, since we again need to bisect into 2 equal half, I can write it as 6 by 8 and this one as 2 by 4 as 4 by 8. So, the middle point will be 7 by 8. I can label it as 0 and this one as 1. But now onwards 3 by 4 will be the last point of the interval 1. So, every term if we keep on dividing, it will always be in the last interval. This is the reason why each terms will be 1. So, remember, if there is any point at any stage, if we have the real number which is sharing the boundary of 2 such intervals, then after some finite digits either all terms will be 1 and after some finite digits all terms will be 0. Just like in decimal system, in 1 by 2 we have seen that after some finite digits all terms ends in 9 or all terms ends in 0, and if it is not sharing the common boundary, then the representation will be unique. So, this is the representation of 3 by 4 into binary form. Similarly, let us do one more question in case of ternary form, because the construction of ternary form will be used in construction of Cantor set, representation of real number into ternary form. So, for this we can take, let us start try to understand with the help of example. The notation we will take 0, 1, 2, the you can take equivalent symbol as -1, 0 and 1 also. So, we will use this these digits 0, 1 and 2, and let us start with, say, so in ternary representation, if you want to represent any real number into ternary form, then I need to divide equally into 3 equal intervals. So, 0 and this one is 1, so I can write it as 3 by 3 and this 0 as 0 by 3. So, the other 2 points will be 1 by 3 and 2 by 3. Again we will do the same technique, we will label it by 0, this one by 1 and this one by 2. Now, suppose we are interested in representing, say, let us take any other number, say 1 by 4 into ternary form. So, clearly its denominator 4 in comparison to 1 by 3, its denominator is greater. So, 1 by 4 will be left to 1 by 3, lies in this interval. So, I can write 1 by 4, the first digit as 1 by 4 is equal to 0, and obviously because we are writing ternary form, so point there will be a point and we need to write into ternary form. Now, question is what will be the next digit. So, again select this interval denoted by 0 and say 1 by 3, divide into 3 equal parts. So, I can write it as 3 by 9, this one as 0 by 9, next will be 1 by 9, this will be 2 by 9, label them as 0, 1 and 2, and then again look at where 1 by 4 will lie. So, 1 by 4 will be in the last part. Just look at 2 by 9. So, 2 by 9, if I can write it as 1 upon 4.5. So, still 4.5, this denominator is greater than 4. So, this 2 by 9 will be less than 1 by 4. This implies that 1 by 4 will lie into this part, and the next term will be 2 because it is lying into the next part. Again select this interval and keep on doing this procedure, we will get the next digit as 0, 2, 0, 2 and so on. So, this is the ternary representation of the real number 1 by 4. And the interesting thing here is that it is not going to involve the digit 1 here. Though in ternary form there are numbers which will involve the digits 1 also, but in Cantor form, Cantor set construction, we will see that we will keep on dividing into 3 equal parts and removing the middle interval. On repetition of such intervals construction, again dividing into 3 equal parts and removing the middle one, and after that we will take intersection of all such intervals, that will be your Cantor set. So, since we have been removing the interval 1, the middle part, so 1 will not be there in representation. So, 1 by 4 is one of the member of Cantor set. This we will look in detail when I will discuss the Cantor set. Another number, let us take another example and express in terms of Cantor set. Let us start with a number which is sharing the common boundary and we are interested to write it into ternary form. Then either after some finite step, again all digits will be 0 or all digits will be 2. So, one such example we can take as 1 by 3. This is 0, this one is 1, I can write it as 3 by 3, again this one is 1 by 3, 2 by 3, label this as interval as box 0, this one as box 1, this one as box 2. Then clearly 1 by 3 is sharing the common boundary. So, I have two choices, either we can denote it by 0 or we can denote it by 1. We can denote it by 0 or the first digit will be 0 or 1. Now, select this one, keep on dividing into 3 equal parts. Then by repeating the similar procedure, we will get the next digit. So, this is the technique which used to represent any number into binary, decimal or ternary form or hexadecimal part. To express in hexadecimal part, we need to divide into 16 equal parts. So, I am giving you some examples. One can express as 1 by 4 into ternary form, as 0.020202 and so on into binary form. Similarly, 1 by 5 you can take it as exercise, and one can use the similar procedure to for its ternary representation 0.121. We can write it as 0.02 into ternary form. This representation is into ternary form, remember, ternary form. And 1 by 6 as 0.01 bar. Now, these examples will help you to understand what is written here in the book of R.G. Bartley. We will discuss briefly to discuss informally the binary representation of real numbers. It will suffice to consider real numbers between 0 and 1. Then the representation of other real numbers can then be obtained by adding a positive or negative number. Now, suppose x is any real number in between 0 and 1. So, we will use the same repeated procedure to associate a sequence an of zeros and ones. For example, 1 by 2. So, because we are interested in writing binary form, so just now we have done this. I can write 1 as 2 by 2 and 0 as 0 by 2, and the midpoint will be 1 by 2, and we have labeled it as 0 and this interval as 1. So, 1 by 2, because it is sharing the common boundary. So, we have two choices, either the first digit will be 0 or 1 into binary form. So, that is what written here, that if x equal to half is the boundary point in bisection procedure, then we may take a1 to be equal to 0 or 1, this notation 0 or 1, and if we take 0, then our first digit, see we are writing x into 0.a1, a2 and so on into binary form, where each digit a1, a2 is either 0 or 1. So, this first digit is obtained by dividing it into 2 equal parts. So, if x equal to half, so this half basically this x will be enclosed in between these two intervals, closed intervals. A1 by 2 is less than equal to a1 plus 1 by 2. Why? Because see, if this x is half here and half is within this interval 0 by 2 to 1 by 2. So, if I put a1 equal to 0 here, then we have 0 by 2 and 0 plus 1 by 2. So, we get this interval 0 by 2 to 1 by 2, and if I put a1 equal to 1 here, then I will get the interval from 1 by 2 to 1 by 2 to 1, 1 by 2 to 1. So, we have enclosed this x into a closed interval. I can write that x belongs to a1 by 2 comma a1 plus 1 by 2, and if x is not sharing the common point, for example, this one, if x is not equal to half, then either it will belong completely to the left half or the right half, and those cases already I have discussed earlier. So, if it will belongs to left half completely within the left half, then we will allot the first digit as 0, and if it is on the right half, we will allot it as 1. So, for the next digit, how to find a2 here? Again we need to keep on dividing by for every next digit, we need to keep on dividing by 2. So, a1 by 2 is the first digit, and this 2 square denote the second division. Suppose we select this interval, then again we will divide into 2 equal half. So, for the second digit, x will be enclosed between these two intervals, Now, in general, at nth stage, x will be enclosed within these two closed interval, And one of the interesting thing is that we always used to write this that this representation is unique. So, using nested interval lemma, we can show that this interval is unique. Why this is unique? Here see, x belongs to for example, at the second stage x is enclosed into a1 by 2 plus a2 by 2 square comma a1 by 2 plus a2 plus 1 by 2 square. And so again in the case of so each of these interval, basically this one is I1, the length of interval from I1 by 2 to A1 plus 1 by 2. Suppose this one is I1, then the next at next stage we are getting I2. So, I2 is contained into I1, In is contained to In minus 1 and so on, and we have the nested sequence of closed intervals. And if we look at the length of this interval, then at this stage if we subtract this whole term from this term, then a1 by 2 will get cancelled out, a2 by 2 square will get cancelled out, and at the second step we have the length of interval as 1 by 2 square. So, similarly at nth stage we have length of interval as say 1 by 2 to the power n, length of interval as 1 by 2 to the power n, and this length is tending to 0. And as per nested interval property, if there is a sequence of nested closed and bounded intervals and their length is tending to 0 or infimum of such length is 0, then the representation will be unique. So, that is what written here, this representation is unique except when we are sharing the it is sharing the common point. But in that one, after some finite digits, if you are writing in binary form, then all digits will be either 0, ends in zeros, or all digits will end in 1. So, each sequence of zeros and 1 is the binary representation of a unique real number. Unique real number, why? Because its length is 1 by 2 to the power n, and as per nested interval theorem, there exists a unique real number which is common to each of the such interval, and this is our binary representation. So, just like in decimal system, we used to keep on dividing by 10 in writing the series representation. Here we will keep on dividing by 2. For example, this a1 is obtained by a1 by 2. How to obtain this a2? At next step we have divided the interval again sub interval into 2 parts. So, it will be 2 square plus a3 upon 2 to cube and so on. At nth stage it will be n by 2 to the power n. So, this is the remark given here. The concept of binary representation is extremely important in this era of digital computers. A number is entered in digital computer on bits, and each bit can be put in one of two states, either it will pass current or it will not. These two states corresponds to the value 1 and 0 respectively. Thus, the binary representation of a number can be stored in a digital computer on a string of bits. Of course, in actual practice, since only finitely many bits can be stored, the binary representation must be truncated, and because the size of memory size is limited, and while we are dealing with machines, or we in practical in file application purpose, we can only deal with finite number of things. And what allows it to truncate? Your density theorem. Q closer is equal to R, that is every real number can be approximated by rationals. So, within this real, either it is rational or irrational, one can approximate it with as close as possible with rational numbers, and we know that rational numbers are either terminating, and if it is non-terminating, then it will be recurring. So, decimal expansion already that I have explained, same thing is written here, this one. So, we have enclosed this x into closed interval, again nesting is there, and length of interval is 1 by 10 to the power n, and it is tending to 0. So, real number representation will be unique. This both of this term one can write it into series form, and both will converge to 1 by 2. So, this concept already I have explained to you. Now, using this we will show that in the next part that the unit interval 0 1 is not countable.